Hi everyone. So we are going to start today with Ansys Fluent, and we are going to model a pipe flow in Ansys Fluent. So I'm going to drag. Okay, so before I can drag this Ansys Fluent, I have to also create a geometry. So let's go to geometry and I'll drag geometry here. And we'll be creating a pipe with different cross-section areas at its end. So let's right click on the geometry and we'll use space clean to create the geometry now. It's opening up now. So we have entered space claim now and we have to create our geometry. So the very first step is to select our plane and we'll select on new sketch plane, selecting the plane. And as we want to create a pipe that has different cross-section areas at its end, and we'll be keeping the length of the pipe to be around 200 mm. So let's first draw a circle that has initial diameter of 20 mm, and now we have created that circle. Now we have to create plane, and we have created the plane, but we'd like to perform something similar to loft operation. So we have to move this plane at around 200 mm. So we'll exit in 3D mode first, then we'll select move and we'll select the plane, and we'll be moving this plane in Z direction at 200 mm, and I'll write 200, press enter. Now I have a plane that is at 200 mm, and now I'll be going into sketch mode again and selecting this new plane to create a new circle that has diameter of, let's say, 60 mm, and now we have a circle that has diameter of 60 mm. Now what we have to do, we have to join these two circles using loft command, and we'll select loft, that is blend in this space claim. So we'll be selecting first circle and now we'll be selecting second, and we have created a loft command by selecting both the circles. We'll click on right and we'll see what we have got. We have got a surface indeed, and we'd like to have a 3D object actually. So I'll move back. Okay, so we have to create the circle again. I'll create the circle with 60 mm diameter now, and I'll be exiting into 3D plane now, and we have two surfaces. I'll be using blend operation again for these two surfaces. I have selected first and use control in order to select both the surfaces, and I'll press enter. Now we have a pipe that has different cross section area, but the problem with this one is it is a solid pipe now. So we have to create a shell in it, and I'll be creating a shell for this body, and we have an option called shell here. So we have to select faces where we'll be removing, and we also have to select thickness. So I'll be selecting both the surfaces with 2 mm of thickness. I have selected the very first one, and I'll be selecting the second one as well, holding control. And now we can see that we have created a pipe that is 2 mm thick, around 200 mm long, and has 20 mm initial diameter and 60 mm final diameter. Now we have created our geometry. So what we have to do is also create and fluid body here, that will be enclosure, and you can find that in the prepare tab here. So if you will see, you have an option of enclosure and you have also an option of volume extract. This is used for extracting inner volume of closed region. So I'll select this and I'll select the edges where I have to create my boundary, and I'll select both the edges or at the ends and I'll create right. And as you can see, we have a volume as well in our geometry. So if I'll hide the pipe part, the solid part, you can see that we have a volume also, and this volume actually represents the volume of water that is being flowing or any fluid that we are going to use in it. So now we should exit space claim, as we have created all the domains that we needed to create. Now we have created the geometry and we have exited into workbench space. Now we'll be dragging Ansys Fluent. So in this we have two options actually. We can either mesh with Fluent mesh, or we can use the normal mechanical mesh and then convert it to Fluent mesh. And I'll first connect geometry, then I'll right click on mesh and left click on edit, and now we'll start with meshing of this geometry. So now we have entered Ansys Fluent for meshing. This is a mechanical part only, but we can use it for meshing. I'll update the mesh and let's see what happens to the geometry. So it's updating and we have done our meshing now. So as you can see, we have created a mesh that is fine enough, and I guess this is good enough. We can move with this sizing, and we have different settings here that uses adaptive sizing, and I guess this mesh is fine, and we'll be moving forward into Ansys Fluent to solve the different equations of pipe. So now that we have created mesh, we also have to provide with name selections of inputs and outputs. So I'll be having this particular point as my input, so I'll click on that and press, let's see, yeah, we have selected the face only. So after clicking on this face, I'll press N and this name selection box will come in front of me, and I'll write at inlet here. So inlet I have written here. I'll press OK. Now I'll be left clicking on this and press N, and I'll be putting this face as outlet. Okay, great. So we can also select this part and I'll name this as pipe. So I'll click on OK, and this is enough, I guess. So we have created the name selections as well, and you can see the name selects here that you have selected and created, and these will be represented in your Fluent as well. So let's move towards Fluent. So now we'll be entering Ansys Fluent now. So we'll be clicking right click on setup, click on edit, and Ansys Fluent is getting started actually. So yeah, we come up with this display on screen that has different controls for us. So we'll be clicking on double precision. It gives us more precise solving answers that we are solving for. We have solver processors, so that depends on number of cores that your computer has. So mine has 2, and I'll be entering 2. This is solver GPUs per machine. So if you have any solver, that is any GPU that is into range of Tesla series of Nvidia, then we can do it. So we'll be clicking on start and moving forward. Now as you can see, we have entered Ansys Fluent, and this clearly shows us the name selections that we have created, inlet and outlet as well. So we'll go into cell zone conditions, and we'll see that that everything that we have meshed for is actually taken as fluid. So no, but this geometry of ours is solid. So I'll right click on it and change it to solid. Now we have it in solid. So it is asking for material, and as of now I'll let it be aluminum. I'll say apply and I'll close it. So now as we do have this Ansys Fluent thing, so what we have to do, we have to select equations that we'll be using, and if we'll enter into viscous model, so we have this several models, and we'll be using K-epsilon because this is the model that is preferred for pipe flows. And if you are doing any external aerodynamics thing, then please go with K omega model. So in K-epsilon we have some settings as well inside it. So we have standard RNG realizable. So standard RNG realizable are into an ascending format of how accurate the model will be. So realizable will be the most accurate of all. I'll be selecting this TKE Prandtl number. These are user defined function, and I'll leave it for now. And I'll be improving my accuracy of this model by selecting curvature correction as well, and I'll click on OK. And we have 2 types of solver here, so we'll be keeping it on pressure based. I'll be wanting it to be steady, and velocity formulation absolute. Now we have to provide with the boundary conditions, and also we have to provide with, fluid is air here. So I'll right click on new, and we'll be opening up materials. I'll be entering Fluent database, and I'd like to have water here, and we have so water will be somewhere around H2O. So we'll go downwards, and yeah, so H2O we have to find. So we have water in liquid form as well. So I'll be selecting this liquid form. I'll be clicking on copy, and as you can see in fluid we have a material as water. I'll be entering cell zone, and I'll be edit this volume, and as of now its material is air, so I'll change its material to water now. I'll be clicking on water liquid, and yeah, we have it. So I'll click on apply, and we have changed the material. I'll keep material of our pipe as aluminum, and let's move forward to setting up the boundary conditions. We'll be setting up inlet of the pipe, and so we have this velocity magnitude. So I'll be entering it to be 20 meters per second of velocity magnitude. I won't be creating any initial gauge pressure to it, and also no absolute thermal condition as well. magnitude will be normal to boundary, absolute reference plane, and I'll apply without changing any further things into it. Now I'll close this, and we have interfaces, we have internal, and I'll select an outlet. I'll double left click on it and see what do we have here. So I will also like to have prevent reverse flow in it, and radial equilibrium pressure distribution. I'll just keep this thing click. We have selected. Now we have ball, so I'll edit on pipe part. Okay, so we don't have anything here. I'll also look at others as well. Let's see. Yeah, I'll be making all the walls as stationary, and I'd like to have conditions as non-slip as well, and I'll apply. That is great. Roughness is also, so I'll be seeing it for all the walls. We'll be seeing it for, yeah, so I guess we have done it. So wall 13 was the most significant things of all. Now what we'll be doing will be entering methods. I'll be into coupled method only, and flux type is also same, and I like to keep turbulent kinetic energy in second order. Pseudo transient flow we'll be considering, and yeah, so we have control like change the solution method that we are going to do. These are some solution controls that, so here are the report definition that we can actually monitor, and we'll move to initialization now. And I'll be selecting hybrid in initialization. I'll select on initialize, and we can see initialization, hybrid initialization is done. We can see in the console part. So we have a condition of 1 to the power minus 1 into 10 to the power minus 6. That is the condition, and we have achieved it much better. So chances of our model getting converged is really high. So I'll double click on run calculations. I'll see for iteration reporting intervals. I'll write number of iterations as 500. We have reporting interval here. Yeah, so we have reporting interval here. We have profile update interval here as well, and we have done initialization. We have everything. We'll click on calculate. So now we can see here that our model has converged here, and I have even tried to increase the number of iterations that I'll be doing, but as the model itself has converged here, so I'll be moving towards plotting different graphs here. So we can actually do it in CFD post as well, but we'll also like to do it here, so let's do it here as well. So I'd like to have it for area and velocity, as we'd like to validate our experiment with the continuity equations, or we can also validate it with Pascal equation as well. So okay, let's say I'll be clicking on inlet and outlet part only, and I'll say okay, display. Okay, so we have this thing, and okay, I'll be changing it to wall 13 as well. Okay, so this I'll be changing it again. Yeah, now we have a very good counter, and we can see that pressure has reduced to almost zero. This particularly means that flow wasn't taking place after this part, and yeah, we can see the pressure here, and I'll say close. I'll also like to add another counter, and that will be for velocity now, and I'll be collecting inlet, outlet, arc regions, and I'll say display. So this is the velocity part that we have. As you can see, this is where some velocity magnitude has changed, and this is where we have highest of velocities. So as I told you, like, flow has almost stopped after a certain point in the pipe. As we can see that velocity has went to zero. This also indicates that our solution has converged and we have got the correct answer for that. I'll say close. We can also like plot vectors, path lines. So I'll plot for velocity as usual, and this is what I'm going to do. So as you can see, this actually contributes to magnitude, and we can see at this point, this is the point where things do get changed a lot. So yeah, I can change to it 3D arrow, cones, or also scale. Like, I'll be making it half, and now if I'll see, yeah, you can see the difference what I have done, and we have magnitude as well. As we have stopped reverse flow, or we could have seen something seriously good here as well, but this is what the requirement was. Okay, I'll close it, and I'll also close this one, Fluent, and I'd like to enter into CFD post part, and I'll click on OK, quit. I'll say OK. I'll right click on edit and left click on edit. I'll be entering into CFD post to see and like do my post processing part of whatever results that I have plotted till now. I'll cancel these things. So let's move forward. So we have entered CFD post, and we can see that we can only see 2 circles here, so no worries. I'll be plotting my counter for pressure as well. I'll enter pressure. Okay, pressure already exists. I'll say pressure 1, and I'll be selecting domains that I have to select. So I'll be selecting, of course, these 4 regions, and I'll be selecting on OK. Variable will be pressure as usual. I'll be seeing what I can do, and I'll see and apply. We can see it very clearly what has actually happened, and this is why actually CFD post is required. You can see like how easily we can see where the flow is getting disrupted, and if you'll see, for only less than half of the pipe's length, flow was able to maintain itself, and it's very easy. If you go deep, you can find it. You can also find your values here. You can see like at this point we have almost stopped. So I'll also like to have for streamline, I'll select the streamline as number one, and domains that I'll be, yeah, so I'll actually be using only volume domain, and this will be starting from inlet only, equally spaced samples, and I'll be doing it for velocity. Okay, so I guess we have to hide it. Yeah, we can see now streamlines here. So what is happening to the flow, and if you will see that at upper part flow, this was also, if we'll see that this was something that we saw when we were in Fluent as well, with by plotting contours on the ends of it. So I'll also like to plot for particle tracks, and I'll put OK. So now I have to select geometry, and so I don't know how to. Okay, so let's say I can't see. Okay, wait. So I will okay, so we can also plot for vectors that I have already shown you. So let's plot for vectors here, and I'll turn off streamlines here. I'll open contours, and I'll have to select locations, and I'll be selecting those 4 locations and click on OK. And yeah, and I have to actually hide contour to see what is happening, and I'll be increasing the factor to 2, and I'll apply. I'll also have to change like exactly symbol size is like have to increase, like yeah, I'll increase, and I'll also change it to arrow 3D. That will give us better idea. Yeah, we can now see that flow is mostly happening in the lower part of the pipe. This is very easy. The end, you can see like what is the magnitude. These arrows also represent magnitude. As we move forward, we can see that magnitude of flow or velocity that we are seeing has reduced a bit, and using this you can actually create a verification as well. So this is it. Thank you guys for watching.